Before we begin our practice problems, I just want to go over this table that discusses the relationship between the voltage of an electrochemical cell, the delta G of a reaction, so the delta G can either be exergonic or endergonic, we call that free energy, and its relationship to an equilibrium. So remember a definition of an equilibrium reaction. It's a reaction that does not proceed to 100%. So at the end of the day or the month or the year, when that reaction is totally complete, you will have some reactants left over, or you'll have some products left over. Now the question is, will you have more products left over relative to reactants, or will you have more reactants left over relative to products? So that in essence is an equilibrium. So there's a relationship between all of this. The equilibrium is really determined by the value of the equilibrium constant. Which one is favored? Are products favored relative to the reactants, or are the reactants favored relative to the products? And of course, Ecell, which is the focus of this chapter, has to do with the idea that certain chemicals can behave like a battery. In an oxidation-reduction reaction, one element gets oxidized to another element, and that serves as the anode. Another element gets reduced to another species, we call that the cathode. We join a cathode and an anode together via a salt bridge, and you can get a battery which registers some voltage, albeit it may be crude. So this is the idea of an oxidation-reduction reaction. Chemicals that can form a redox couple, oxidation-reduction couple, and whether that oxidation-reduction reaction proceeds to the product side is determined whether you have a positive voltage. So if you have a positive voltage, obviously that is a oxidation-reduction reaction that's going to go forward and it's going to favor the product side. Now, if it's an equilibrium reaction, we know that an equilibrium that's much, much greater than 1 is also a reaction that favors the product side. Now, in terms of thermodynamics and energy, the delta G, which is the Gibbs free energy, that is negative. So a negative reaction, negative value, of delta G is an exergonic reaction, and it's a reaction that favors the products. It releases free energy that can be utilized to do other aspects. So it's energy that's useful. So all of these things, an equilibrium constant greater than 1, much, much larger equilibrium constant favors the formation of the products. A positive voltage, now that should come as natural intuition that if you have a positive voltage, you're going to have a cathode and anode battery that works. A free energy that's negative, we call that an exergonic reaction. Energy is released and the products are favored, and that equilibrium or the reaction favors the product side. Now, on the flip side, you can have a negative voltage for your redox cell, and notice the not symbol, that little superscript O, means that this is measured at standard state conditions. If that voltage is negative, again, natural intuition should tell you that it's a dead battery. The oxidation-reduction reaction is not favored. The delta G in terms of thermodynamics, that's a positive value in kilojoules per mole or joules per mole, and we call that an endergonic reaction, and a reaction that is not go. It's a reaction that favors the reactant side. And also from an equilibrium perspective, a low equilibrium value, less than 1, implies that the reaction is favoring the products. Very little product formation. More and more of the reaction stays along the reactant side. Now, if the equilibrium constant is equal to 1, you're neutral. So that means there's no voltage that's registered in your anode or cathode battery. The delta G of the reaction is 0, so it's not endergonic or exergonic. And the equilibrium is essentially 50-50. So you have reactants and products. Nothing is swayed relative to the other. Nothing is favored relative to the other. So one final point here is that a large equilibrium constant, a positive voltage, a negative free energy, all of that favors the product side. All of those things corroborate and substantiate one another. So the equilibrium constant, the value of your Ecell and voltage, and your Gibbs free energy always substantiate and always corroborate one another. They will never contradict one another. They support one another. So if your equilibrium constant is large, that means the reaction favors the products. It also means if it's a oxidation reduction reaction, it means a positive voltage and it means a negative free energy. Gibbs free energy of negative, you have to realize that it's an exergonic reaction. Energy is released, products are favored. So these are three equations in this triumvirate that sort of relate the thermodynamic parameter delta G, the equilibrium parameter constant, equilibrium constant K, and then standard state energy of the cell, E of cell. So all of these are at standard state conditions, and these are the equations that sort of relate one to the other. So if you know the equilibrium constant K, you should be able to get the Gibbs free energy. Temperature is also important. R is your gas constant. And also for this equation here, F is your Faraday constant, 96,500 joules per volts. Faraday constant F and gas constant R are constants that will be given to you on an exam. The problem is determining whether an oxidation reduction reaction is spontaneous or not. By spontaneous means that it delivers a positive voltage. So in an electrochemical cell, you have an anode, which is the site of oxidation. Here, some chemical A gets oxidized to something else. And you connect it to a cathode where some chemical B gets reduced to some other species. So you join them together, you get a battery. That battery composed of an anode, site of oxidation, combined with a cathode, site of reduction. If it gives a positive voltage, then you have a spontaneous reaction. So the first thing you want to do here is check to see what gets converted to what. So here we have copper going to copper plus 2. And then we have iron plus 3 going to iron plus 2. So we'll just avoid the stoichiometric coefficient. We'll just avoid the 2 to balance the equation. However, the equation is balanced here. So 2 times 3 is 6, so plus 6 on the reactant side, plus 2, and then 2 times 2 is 4, so 4 plus 2 is plus 6. So we have plus 6 both. What I'm going to do here is find the reduction potential of copper going to copper plus 2. In order to do that, we will look up our standard reduction potential table. So we have copper going to copper plus 2, and so here we have copper going to copper plus 2. Well, it's the reverse of what we see here in our standard reduction potential table. So here's our potential. Copper going to copper plus 2. This is the reverse, so if it's the reverse, we're going to flip this, and when we flip this, we flip the plus 0.34 volts to minus 0.34 volts. And then Fe plus 3 goes to Fe plus 2. So let's see where that is in our reduction potential table. So Fe plus 3 going to Fe plus 2 is positive 0.77 volts. So we're going to keep it as is because in our problem, it's plus 3 Fe going to plus 2 Fe. So here are our two half reactions. If we combine this and this, we should get that, our original problem in our original reaction. We need to cancel out the electrons. So in order to do that, we're going to multiply the bottom half by 2. So if we multiply the bottom half by 2, this is a reduction half reaction. The 2 electrons on this side will cancel out with the 2 electrons on the opposite side. So we'll multiply the bottom by 2 and then add them up together. We multiply the bottom half reaction, this reduction half reaction, by 2. That's what you see here. Now we'll add those two together. This 2 electrons will cancel out with that 2 electrons there. One's on the product side, one is on the reactant side. And when we add it all up, we add the voltage, we get 0.434 volts. That voltage is, we get 0.343 volts. That voltage is positive. This is a spontaneous reaction. We would expect a battery consisting of copper and iron plus 3 to be valid and register 0.43 voltage. So in this one, copper is being oxidized. It's losing 2 electrons. Those 2 electrons are being gained by Fe plus 3. How about this reaction here? Here we have silver solid going to silver plus. And let's take a look at that half reaction. Silver solid going to silver plus. So that's right here. Silver solid going to silver plus. The problem is, so here we have the half reaction for silver plus going to silver solid. The original problem is the opposite. It's having silver solid going to silver plus. So we're going to flip this half reaction, make it oxidation instead of reduction. And when we flip this reaction, we're going to flip the sign. So this is the oxidation reaction from silver going to silver plus. We lost an electron. And the other half reaction, well, it obviously has to be oxidation. If this one is, it obviously has to be a reduction. If this one is oxidation, then zinc plus 2 going to zinc solid is a reduction. So let's figure out and look up how much voltage is associated with that reduction half reaction. So that one is listed right here at minus 0.76 volts. We're going to keep that the same, no flipping, because this is exactly what is happening in our problem, zinc plus 2 going to zinc solid. So minus 0.76 volts for the reduction half side of the reaction, negative 0.80 volts for the oxidation side of the reaction. Let's cancel out the electrons. In order to do that, we'll multiply the top half reaction by 2 and then add them up. So we multiply this top half reaction by 2. The voltage stays the same. We do not change that voltage. After multiplying this by 2 and canceling out the electrons, this is our final answer, which is the same thing as the original problem. But adding up those voltage, we're getting minus 1.56 volts, negative voltage, something that's not going to happen. So this is a reaction that is not positive. So we do not expect silver to get oxidized to silver plus, and we do not expect zinc to get reduced to zinc solid. If you look at it in the positions of the redox potential table, so here is silver, and then zinc is down here, so we would expect the opposite. So we would expect the opposite. We would actually expect silver to become reduced and in turn flip this zinc to an oxidation half reaction. For our final reaction here, we have mercury going to mercury plus 2. Notice we balanced this equation here. So mercury liquid going to Hg plus 2. Let's check where that is in our reduction potential table. That's right here. Mercury going to mercury plus 2. That's the flip of what we see here. So that's minus 0.85 volts. We're going to have to flip this. So mercury going to Hg2 plus 2 is minus 0.85 volts. And H plus going to H2 gas is our second half reaction. That's got to be a reduction if this one was oxidation. Remember, for every oxidation, there's a reduction. So H plus going to H2, that's a 2 electron transfer. That is our reference point 0, so this is associated with 0 voltage. And the 2 electrons on this product side here are going to cancel out with the 2 electrons on the reactant side here. And we'll add those two reactions together, add the voltages, minus 0.85 volts, non-spontaneous. In fact, we would expect the opposite. Looking at the positions in the standard reduction potential table, we would expect Hg2 plus 2 to be reduced and cause this to flip and become oxidized. Again, the rule is, the diagonal rule is you take one reaction, half reaction here, causes everything below it to flip to become oxidation, and that will register a positive voltage. Our second problem involves calculating the free energy, Gibbs free energy, for a reaction. So if that value is negative in kilojoules or joules per mole, we have a reaction that proceeds to the product side. It's called an exergonic reaction. If that value of delta G is positive, we have an endergonic reaction, a reaction that stays in the reactant side and does not move forward. So in this reduction oxidation reaction, we have Au going to Au plus 3. So let's look where that is in our reduction potential table. For the time being, let's just ignore these coefficients that are in front of the chemical. So Au solid going to Au plus 3 is the flip of what we see here in our table. So we're going to flip the voltage. This is going to be minus 1.50 volts. And so this is an oxidation reaction. For Au to become Au plus 3, there's a loss of 3 electrons. And then calcium plus 2 going to calcium solid. Let's see where that is in our reduction potential table. So calcium plus 2 going to calcium solid is minus 2.87 volts. So we're going to keep that as is. So we need to cancel out our electrons. So we're going to multiply this side by 2, which is 1/2 reaction. And we will multiply the bottom half reaction by 3. And that will give us 6 electrons that are going to get canceled out. So this is a 6 electron transfer reaction. So 6 electrons are going to be transferred. And adding those two half reactions up, adding this, we'll get negative 1.37 volts. That's Ecell at standard state. The delta G naught, let's go back up to our triangle here. Delta G naught, let's use this one here. Delta G naught equals minus NF Ecell. F is the Faraday constant at 96,500 joules per volt. So delta G naught is minus NF Ecell. So N is 6. F is 96,000 joules over volts. That's the units, joules over volts. And E cell is minus 1.37 volts. The volts cancel. And we're getting about 79, or I'm getting about 793,000 joules. And converting it to kilojoules, it's about positive 793 kilojoules. So negative voltage, non-spontaneous, a dead battery, positive delta G, endergonic reaction, a reaction that does not favor the product side. Our next problem here is writing the galvanic cell notation and calculating E cell at standard state, and if it's spontaneous or non-spontaneous. So don't forget our rule here. A galvanic cell can be written as the anode, and this two lines represent a salt bridge, and then the cathode. So this anode is the site of oxidation where you lose electrons, salt bridge. The cathode is the site of reduction where you gain electrons. So here we have Cr solid going to Cr plus 3. Let's write that half reaction looking at our table. So here we have Cr going to Cr plus 3. It's the opposite of what we see here in our reduction potential table. So we're going to flip this to get what's in our problem. All right, how about nickel plus 2 going to nickel solid? Where does that fall in our table here? Nickel plus 2 going to nickel solid. Nickel plus 2 going to nickel solid minus 0.25 volts. So let's put that in. Like our previous problem before, to cancel out the electrons, I'm going to multiply. In doing so, I'm going to get 6 electrons that are going to cancel out on the top side with the 6 electrons that will cancel out at the bottom side. And this is a 6 electron transfer reaction. So multiplying this top one by 2, the bottom one by 3, and we cancel out the 6 electrons. So this 6 electron will cancel out with that 6 electrons. The voltages stay the same. We'll add them up. I'm getting about 0.494 volts. It's spontaneous. And then finally, how do we do this galvanic cell notation? It's the anode couple. That's going to be chromium to chromium plus 3, salt bridge, cathode couple, nickel plus 2 going to nickel. So here's our galvanic cell notation. So a couple of points I'd like to tell you here. Number one, it's okay if you add the 2 and 3. If you add it, that's fine. If you don't add it, that's just as well. It's not a big deal adding the coefficients. But the second, and this is probably the most important thing, from here, you should be able to straight up go from there and vice versa. Okay, so if I give you this, you should be able to write that. If I give you the galvanic cell notation, you should be able to get from that the balanced oxidation reduction reaction. Problem number 4 employs utilizing the Nerst equation. So the Nerst equation is basically calculating the voltage under non-standard state conditions. So standard state conditions would mean the concentrations are usually set at around 1 molar, temperature 25 degrees, whatever standard state is. Non-standard state conditions, you could automatically tell, okay, 0.10 is not standard state, and 1.90 molar for zinc plus 2 is not standard state. So, these voltages, going back to our potential table, these voltages are at a specific condition, and actually it's 1 molar. So in this problem, we don't have 1 molar, we have all these weird concentrations. So we're going to utilize the Nerst equation. Q is the same thing as K. It's used to compare to K. It's the products over reactants. We omit solids. All right, let's attack this problem here. Copper plus 2 going to copper solid. What is that? In our table, copper plus 2 going to copper solid, positive 0.34 volts. So let's write that out. And zinc solid going to zinc plus 2. Let's write that out. Probably we're going to have to switch it here. Zinc solid going to zinc plus 2 right here. Zinc solid going to zinc plus 2. Positive 0.76 voltage. We're going to flip this, and that's going to be positive 0.76. All right, so we got our two half reactions. The top one is a gain of 2 electrons. The bottom is a loss of 2 electrons. We can easily cancel out the 2 electrons here with the 2 electrons there. Add them up, we'll add up the voltages, and we're going to get about 1.10 volts. So adding up these two half reactions, and we get our original problem, but now we know the voltage is 1.10 volts, spontaneous. Let's calculate Q, products over reactants. It's going to be the concentration of zinc or the concentration of copper raised to the power of 1, right? So it's not squared, it's not cubed, it's just raised to the power of 1. So Q is products over reactants. I'm getting about 19. So let's plug that into our Nerst equation. Ecell is 1.10 volts. N is a 2 electron transfer reaction. So utilizing the Nerst equation, I'm getting a value of about 1.06 voltage. It's spontaneous even under non-standard state condition. So let's look at practice problem number 5. Here we're finding equilibrium constant K from Ecell. So reading it, many procedures determine mercury levels in environmental samples involve reducing diatomic Hg2 plus 2 ions to elemental mercury using Sn plus 2. Use the appropriate E sub naught values from the reduction potential table to calculate the equilibrium constant. Okay, that's K at 25 degrees for this reaction. So the first one is Sn plus 2 going to Sn plus 4. So let's find that out in our table here. Sn plus 2 going to Sn plus 4. Sn plus 2 going to Sn plus 4, that's the opposite of this. So we're going to flip this and flip that. So it's minus 0.13 volts. So this is an oxidation half reaction. And so if this is oxidation, the other one has to be reduction. Hg2 plus 2 going to Hg. Let's look that up and see what we get. The Hg2 plus 2 goes to 2Hg liquid, 2 electrons gained, positive 0.85 volts, excuse me. So we wrote our two half reactions. This is a 2 electron transfer reaction, and the 2 electrons at the top cancels with the 2 electrons at the bottom. Let's add these guys up and then add those two voltages together and get our net equation. Adding these two guys up recapitulates the original problem, but we got our voltage 0.72 volts. How will we get K from here? Let's go back up to our triangle of equations. K, I think we're going to have to use this one. E cell is equal to RT over NF natural log of K. R is a constant, will be given to you. F is a constant, will be given to you. N, the number of moles of electrons transferred, is a 2 electron transfer reaction. From this, we can solve for K. We already just now calculated E of cell. So here's our equation that we just calculated. R is 8.314 joules per mole Kelvin. T is 298 Kelvin. Okay, we got that from there. And then 2 electron transfer reaction. F is 96,500 joules over volts. That's just a constant. Natural log of K. So E cell we just calculated at 0.72 volts. So let's put in 0.72 volts here and then isolate K, solve for K. Putting in 0.72 volts here, we're going to isolate K. We're going to have to actually find a way to get rid of that natural log as well. So now I just remove the units. Remember, K is unitless, so really now units are meaningless in this context because K, equilibrium constant, has no units. So 0.72 times 2 times 96,500, we'll divide it by 8.314 times 298. All of that must equal natural log of K. So so the inverse of the natural log is called E, and E to the power of natural log K is K. E to the power of this monstrosity, we'll calculate it in our calculator. So taking E of both sides of the equation, like I said before, E to the natural log of K is just K. E to the natural log of this stuff, I just do that in my calculator, and let's see what we get. I'm doing that on my calculator. I'm getting a value of K as being 2.28 times 10 to the 24. So very large number of K. Positive value of voltage, 0.72 voltage, yes, they substantiate and reaffirm one another. Positive voltage means it favors the product side. A very, very large equilibrium constant also means the equilibrium favors the product side. So we would expect Sn plus 2 to be oxidized and in turn reducing Hg2 plus 2 to Hg liquid. So looking at it here, Hg2 plus 2 is here, Sn plus 2 to Sn plus 4 is right here. So yeah, we would expect this to flip it. We would expect this to stay the same and flip this to Sn plus 2 going to Sn plus 4.